In this video, we're going to look at approximating the value of trig functions. So rather than using those tables that we've built in previous videos, we're going to start using the calculator to evaluate some of these. Please be aware if the directions of a problem indicate to find the exact value of a trig function, you should not be using your calculator because your calculator is going to spit out a decimal and the exact value is probably going to be involving a square root of 3 or a square root of 2, like we've seen in past examples. So we want to find the function values with the calculator, rounding to 4 decimal places. So we want to find the function value for sine of 38 degrees, 42 minutes. In previous videos, I did mention there is a way to type in 38 degrees, 42 minutes and have it interpreted correctly using the TI-84. But we're going to be utilizing our free online graphing calculator, Desmos. So we do have to rewrite this like we have similarly because it doesn't have that functionality. So we're going to find sine of 38 degrees plus 42 over 60 degrees. And I'm also going to set up example B, and that way we can go straight to Desmos and I can show you both of those examples at one time. Cotangent of 183 degrees, 48 minutes. The first thing I want to point out is that we do not have a cotangent button on our calculators. We just have tangent. So we have to use that reciprocal identity. So cotangent of 183 degrees, 48 minutes is the same as 1 divided by tangent of 183 degrees, 48 minutes. And we're going to rewrite that argument the same way we did in example A. So 1 over tangent of 183 degrees plus 48 over 60 degrees. So here I have Desmos pulled up, and I'm just going to illustrate how we would type this in. So and when you open up your Desmos app, you're going to notice that you've got in the lower left-hand corner of this keyboard, we're going to need to use that to find our trig functions. You can just type sine, but I like to go through this menu option. So we're finding sine of 38 plus 42 divided by 60. Now, one thing we want to be very careful of when we're using our calculator, and we'll add this to our notes, is we want to check the mode. So let's make sure that this is actually evaluating 38 as degrees. So I'm going to go to the settings here. And at the very bottom of this settings page, we do have an option for radians or degrees. We haven't introduced radians, but they're coming. So we notice here that this actually is not measured in degrees. We want to go ahead and toggle over. And if you notice now our answer has changed and now it is representing our answer in degree or the value of sine for a degree measure. So this is going to be 0.6252 if we round to 4 decimal places. Okay, let's do the next one. We have 1 divided by tangent of 183 plus 48 divided by 60. And one of the things that I love about Desmos is just that we're seeing this displayed exactly like it's written on our paper. It's a really great way to make sure that we're typing it in correctly and that the answer that the calculator spits out, we can trust. So again, we did have it in degrees. I'm just going to check it again, but just so you're aware, once you put your mode into degrees or radians, it will stay there until you change it. So that's why it is always a good idea to double check what mode it's in. So this is equal to 15.0557, rounded to 4 decimal places. The next thing we're going to look at is trying to find an approximation for an angle measure. So in the examples above, what we did was actually find the trig function value. Now what we want to use, or what we want to do is find the value of the angle given the function value. So we're going to use inverse trig functions, which we're going to learn more about inverse trig functions later in, I think, Unit 3. But this is just going to be for purpose of finding angles using our calculator. So our inverse trig functions on our calculator look like sine with this little -1 exponent, which from an algebra course, that -1 exponent actually oftentimes does refer to an inverse. Cosine inverse and tangent inverse. Just like with our normal calculator functions, we do not have one for cosecant, secant, or cotangent, so we would use those reciprocal identities in this case as well. Use a calculator to find an angle theta in the interval from 0 to 90 degrees that satisfies each condition. Tangent of theta equals 1.4739716. So to do this, we're going to isolate theta, or to solve for theta, theta is going to be equal to tangent inverse of 1.4739716. This inverse is really the same thing as we've learned about inverses in our college algebra classes, and maybe even before that. We use inverses all the time whenever we're solving equations to isolate a variable. So a quick aside, if we have 2x equals 4, to isolate that x, what we're really doing here is taking the inverse of multiplication, because 2 is being multiplied by x. So the inverse of multiplication being division, and that's what allows us to isolate that variable. Over here, what we're really doing is saying, well, let's take the inverse of tangent theta of both sides. And I'm not going to write that whole decimal out for the purpose of this. But then when we take the inverse of that function, that's what isolates theta. So again, let's set up the next one before we shift over to Desmos to see how we would type this into our calculators. Secant theta is 2.749622. Since we don't have a secant function on our calculator or an inverse secant, we're going to transition to cosine. Secant is the same as 1 over cosine. And if we were to manipulate this equation to get cosine out of the denominator, we would end up with cosine theta is equal to 1 over 2.749622. And then to solve for theta, we would use inverse cosine. Now, to point out quickly before shifting over to Desmos again, the directions are asking for an angle from 0 to 90 degrees. So we do want to make sure that the mode of our calculator is set to degrees. So another quick check, we're in degrees, great. It's an easy enough check to do just to make sure. For our first one, we wanted to find inverse tangent of that 1.47 number. So I'm going to go down to our functions tab again. And oh, actually, I didn't realize this. Desmos does have all of our trig functions, which is kind of handy. So I guess there's going to be some pros and cons, whether you're using the TI-84 system or you're using Desmos. But we're going to operate as if we don't have it, just to make sure that this is equitable for all students. So we're going to pull in our inverse tangent function and type in our argument 1.4739716. And that gives us theta is equal to 55.8455 degrees. It says round to 4 decimal places. And then we'll do our second example, which was inverse cosine of 1 divided by 2.7496222. That gives us, let me double check, make sure I wrote that. Oh, I don't see. I typed this incorrectly, so it should be 7,496,222. Okay, that answer looks right. So we get theta is equal to 68.6732 degrees. In this next example, we're going to shift to finding two values for theta between 0 and 360 degrees that satisfies each condition. Sine of theta is equal to 0.92718,385. So using our inverse trig functions, we can find that theta is equal to sine inverse of 0.92718,385. And I'm going to round this to the nearest degree, so theta is equal to, using our calculator, 68 degrees. Now, from here, we want to find another angle. So this is just between 0 and 90. If we think about what this picture looks like, we have our angle theta here of 68 degrees. And remember, our y value does, or excuse me, our sine, the trig function for sine corresponds to that y value. Well, if we were to continue to move over and look at this angle over here, from here to here, it would have that same y value, which would be the same value of sine. So to find that second angle, we're going to take 180 and subtract 68. And that follows, let me think about how I want to explain that. This angle is also 68 degrees, which is why our pink angle, we're going to call that theta 1, theta 2 is going to be 180 minus 68 degrees, or 112 degrees. Now, something that we haven't done is we could check this. We could check by evaluating sine of 68 degrees and sine of 112 degrees. When you look at these on your calculator, we do get approximately that same decimal that we started with. Tangent theta is 1.2348971. So to find theta, or theta 1 in this case, we're going to use inverse tangent of 1.2348971. I like these examples with these long decimals because real life doesn't deal with pretty numbers. So we do have to make sure that we're paying really close attention, taking our time and making sure that we typed the argument in correctly. So we find that theta 1 is about 51 degrees if we're rounding to the nearest degree. Now, to find our second angle, we're going to do a similar graph. So we've got our angle of 51 degrees here. And because tangent is positive, we know tangent is positive in the first and the third quadrant. So what we're really going to see is that this angle is also 51 degrees. And the angle from standard position to that new terminal side will have the same value of tangent. So that means to find the second angle measure, we're going to take 180 degrees. We're going to add that 51 degrees to it. So theta 2 is 231 degrees. And again, you can check the same way we checked in that previous example, that tangent of 51 degrees and tangent of 231 degrees yields that 1.23 value. Now we're going to start getting into some of our applications of these trigonometric functions. So the first one is going to be dealing with grade resistance. So when an automobile travels uphill or downhill on a highway, it experiences a force due to gravity. This force in pounds is the grade resistance and is modeled by the given equation. The grade resistance is equal to W times sine of theta, where theta is the grade and W is the weight of the automobile. If the automobile is moving uphill, then our theta is positive, and if it's downhill, then theta is going to be negative. And we have some figures to illustrate that. Calculate the grade resistance to the nearest pound for a 2,100-pound car traveling at an uphill grade traveling an uphill grade of 1.8 degrees. So we're using that formula, F is equal to W times sine of theta. We are solving for F. W is the weight of the vehicle, so 2,100 pounds times sine of 1.8 degrees. And when we evaluate this in our calculator, we get 66 pounds rounded to the nearest pound. Calculate the grade resistant to the nearest 10 pounds. So we want to be careful here. Our rounding has changed a little bit. For a 2,400-pound car traveling a downhill grade with theta equals negative 2.4. So F is equal to W times sine of theta. Our grade resistance is equal to the weight of the car, 2,400 pounds, times sine of negative 2.4 degrees. So this is approximately negative 100.5. But since we're rounding to the nearest tenth, what we're trying to do is decide, is this closer to negative 100 or negative 110 in terms of the pounds? So the tenth of a pound. It is closer to that negative 100. So our force is negative 100 pounds. A 2,600-pound car is traveling downhill and has a grade resistance of negative 130 pounds. What is the angle of the grade round to the nearest hundredth? So starting with that grade resistance formula, now we're given the grade resistance, which is negative 130, and the weight of the car, but we don't know that angle of the grade. So we're going to isolate sine of theta, dividing both sides by 2,600. Simplifying and just getting a decimal, negative 130 divided by 2,600 is negative 0.05. And then that means that theta is equal to inverse sine of negative 0.05. Using our calculator, theta is equal to 2.87 degrees, rounding to the nearest hundredth.